specifically some examples, and those examples would be what I would include in your foldable. So when I say enthalpy, what symbol do you guys think of? Enthalpy. Say again? Delta H, right? Triangle H. So delta H is the symbol for enthalpy. And that's just expressing the amount of heat either absorbed or released throughout the reaction process. So if a reaction is endothermic, I'm telling you the delta H is positive. Does that mean overall energy is absorbed or released? Absorbed. So I like to give you a couple of words to indicate the same thing, because you really never know which terminology they'll stick with on our exam. So if you are writing down a reaction and heat is absorbed, it's actually acting like a reactant. So an example could be A plus B plus 100 kilojoules, meaning a specific amount of energy, like it could be 50, 100, whatever, yields C plus D. So that reaction, as it stands, the energy is in the reactant, so it's showing it's absorbed, therefore it's an endothermic reaction. For the exothermic reaction, we have a negative delta H, so what would be the terminology we could use here? Released, so energy is released. And how could I rephrase this reaction? So put it to the 100 on the product side, right? A plus B yields C plus D plus 100 kilojoules. Okay, so if I were holding both of these reactions, holding the endothermic reaction in a test tube or a flask or a beaker, and this was happening, and your hand was around it, what would it feel like to you? Why would it feel cold? Ooh, but it would feel cold, the lack of kinetic energy. Woo! That was the coldest one. Thanks, Wesley. Okay. So
it would feel cold because the heat is being absorbed from your hand.
Right, there's a heat transfer here. Anytime you have a reaction, there is a system and a surrounding. There is a component where it's being taken from and a component where it's being added to. So the heat's actually flowing from your hand to this container where the reaction's occurring, because this reaction needs energy. It needs energy to absorb, to actually process the reaction. So your hand feels a lack of energy. Right? Is that a better way to say it? Okay. So that's a nice hand picture. Let's do that for the other one. If you have a beaker and the reaction's occurring, how would it feel to you? It would feel warm. Where is the energy being transferred? Right, here's your hand holding the beaker. This is exothermic, so it's releasing energy to the hand, which is going to make it feel more hot. Okay, so what we like to do is we like to do calculations actually with enthalpy, not just calculating like Q or total amount of energy it takes to melt something, but actually stoichiometrically, so like with a reaction. Hence why we have these reactions here. So whenever you're looking at enthalpy, sometimes it's written as per 1 mole of whatever the reactant product is, and other times we have to actually consider the number of moles expressed by the coefficient in a balanced chemical equation. So we're going to go ahead and look at one of those now. Pull out the lecture notes I provided you, because the examples are there. And I'll go back to one other thing first before we move on. We're only going to, basically this is our last slide of notes for this unit. So I believe it's on the back side. I think I printed, yeah. It says thermochemical equations. Use textbook enthalpy values, formation values. So notice all these reactions up here. We have a delta H reaction, delta H solution, delta H fusion, delta H vaporization. What's the benefit of all these little descriptors? What's it telling us? Riley? It's just kind of just telling us like what's happening in that reaction. Like this is literally a reaction, hence we have a delta H reaction. Where that little negative thing supposed to be there. Is this a reaction? Is this a chemical reaction? No, because it's water gas going to water liquid. So what's it really trying to show you? Phase change. So it's trying to say this is a physical process that's not truly a chemical reaction. But hey, energy is still exchanged. Energy is going to be transferred. So you guys can do this one. Gas to liquid, endo or exo? Okay, so we're going from high kinetic energy to medium kinetic energy. It's going to release that energy. Therefore, it's exothermic. Okay, solid to liquid. So it's going from a low kinetic energy to a medium kinetic energy. It's got to increase that energy by absorbing it, therefore positive. So we've added the signs there. The rest of these, like this is a solution process. We have some solid, we're adding a little water to it to dissolve it, and then it's going to become aqueous. Again, that's kind of a physical process, so we call it H of solution to indicate the solution process is kind of like the descriptor of what's occurring. And apparently when that occurs, it gets really hot. It's like when you're holding that solution, you drop some sodium hydroxide in some water, that baby gets hot. It's releasing over 400 kilojoules of energy. I've done that before. You have to put in ice bath to keep it cool. Okay, so you have the data here. We're going to utilize that. So for question 1, how much heat is lost or gained from the decomposition of 0.25 moles of sodium bicarbonate? Okay, so this was just a stoichiometry question. What do I have to start with? What must I start with? What's the given provided information? Okay, so I have to start with this single number, 0.25 moles of sodium bicarbonate. So we're starting there. Okay, we're going to write our little railroad track fence posting. So in this question, in this series of questions, everything depends on the information above. So I'm going to scroll back up. Tell me which of these is the relevant reaction this is pertaining to. 1, 2, 3, 4, 5. 2. The decomposition of sodium bicarbonate. This is the one. So what's the relationship it's giving us between heat and sodium bicarbonate? What's the relationship? 2 moles. So as 2 moles decomposes, it's doing what with that kilojoule? It's absorbing that much energy, right? So that's the verbal relationship we can make. For 2 moles of sodium bicarbonate decomposing, it's going to absorb 129 kilojoules of energy. That is the ratio. It's basically like a mole ratio, but it's with energy now because we actually have energy data. So when it says how much heat is lost or gained, well, we know now, what is it? It's gained because it's an endothermic process. How much heat is lost or gained from decomposition? 0.25 moles. So what's this ratio I must embed here? What goes on top? 129 kilojoules of energy is absorbed for every what? 2 moles of sodium bicarbonate. So all you're doing is just pulling ratios provided, put them in the right place so the units cancel, just like always. Moles of sodium bicarbonate, moles of sodium bicarbonate. You guys can maybe do that. Yeah. 16, 17. 16.125 kilojoules. Yep. And that's going to be how many sig figs should we record? How many sig figs? Come on. Hold on. 2. This is the data. This is the data provided. This was a ratio we grabbed. Ratios are not like 2 sig figs. The number on top I need, but not this number here. So I need 2 sig figs, so that's 16 kilojoules. Okay. And let's try one more so that I know you get the hang of it. We're going to go down to, let's do 2. Go ahead and do 2. Remember, one equation is going to apply, not all of them. So it's usually right equations. Meaning like balance and completeness. Bailey, pass the calculators out. Thanks, Bailey. Touchdown, gentlemen. He's moving fast though, so if you need one, your hand better be out there. Grab it. All right, Bailey, what do you think we should start with in this question? 406 Kilojoules, okay, of heat. Okay, everybody, what equation is applying here? Which balance chemical equation? What number? The fifth one, the one with water, right? Because it's asking about water. So we have this much water, 1-to-1 ratio, grams to, or gas to liquid. And this is the energy associated with that process. So how many grams of liquid water will be formed from the addition or removal of that much energy? So what's the next logical thing I need to at least write on the bottom? Right, kilojoules, right? This amount of energy in kilojoules, because the kilojoules need to cancel. So that's 40.7. Notice I'm not putting the negative, because if I put a negative here, it's going to end up with a negative mass. Is there such thing as negative mass? No. So which word is going to be appropriate here? Remove, because it's talking about the releasing process. And this is 40.7 kilojoules per what? 1 mole of H2O. Good. And in this case, it doesn't matter if it's liquid or gas. It's just a mole of the compound. Okay. So we're getting to grams. So what's our next step, Bryce? Okay. And can you approximate that? 18.02 grams of water. Okay, gotcha. Thank you. And our kilojoules should cancel. Our moles of water should cancel. And ready when you are. 201.89. So 201.89 grams. How many stick figs do I have? Looks like 4, and well, this one's got 3, so I'm gonna go with the delta H. It is a measurement that was taken, so let's go with 3 here. So this would be what? 202 grams. Good. All right, let's pause there for a second. On the back of your foldable, whenever you're ready, some of you guys maybe aren't through because maybe you looked on my samples up here. Did you guys ever draw something on the back? Probably has the endothermic curves and exothermic curves. Okay, I'm going to just review that real quickly so I know that you know what we're talking about. All right, so on this curve here, I just want you to talk in your groups what you know about it, what you know about the reaction. You should probably discuss is it endo or exo. Well, it can't be both though. Alright, so if you don't have a curve drawn like this in the back of your foldable, this is going to be one that you should draw, and then we'll draw the opposite one as well. So 2 points. This is like we're getting to the point now where we see a lot of graphs, and we see a lot of curves, we see a lot of things that we have to interpret graphically. So it's like maybe in like a week or two, we'll do a quick review of all the graphs we've seen over the last month, because you'll need to be able to interpret those very quickly and effectively. So potential energy is on the y-axis, and it's usually time, or this actually is called a reaction coordinate, but time is usually on the x-axis. And what this reaction is indicating to us is that the reactants have low energy, potential energy, and apparently, because the end is higher, the products have higher potential energy. Well, how would one get from low energy to high energy? What happened over the course of this reaction? It absorbed or gained energy. And so if you're absorbing energy or gaining energy, what kind of process are you? Absolutely, endothermic. Okay, so my delta H would be positive or negative? Positive. What your job is to do is to identify what is the delta H, what is the change in energy over the course of this reaction. So if you had to label the delta H, you would label it as the difference, mathematical difference between the products and reactants. So from about yay to yay, right there is your delta H. And notice it's a positive number because you're going from a low to a high, so you're going up on the graph. Therefore, it should be a positive entity. And as we approach the end of the year, we are going to start to label other parts of this, so I'll just go ahead and tell you one other part you can label now. Who's ever heard of activation energy? Okay, who's ever heard of an enzyme? Okay, what do enzymes do in the body? Speed up chemical reactions. That's kind of like the really generic phrase. Yeah, they speed up chemical reactions, but how? Right, they lower the activation energy of a reaction. So that actually what happens is the activation energy, which is the energy it takes to spark this reaction, is from where the reactants begin to this peak right here. And so we call that EA. EA means activation energy. But I'm not holding you responsible for that yet, but it will be here in like less than 2 weeks. Okay? So that's another piece of the graph we can label. Go ahead and draw the exothermic version of this. Label the same thing. The exothermic version of this. So draw it in there for me, those of you who already have them. Let's see. All right, so we're starting relatively medium to high, and we drive up the hill and then fall down, way down. Okay, so this is going to be exaggerated, but it's going to go way down. So reactants start here, products end way low. Where is the delta H? Between what two letters? R and P, right? So the energy difference between the reactant energy and then the product energy right there would be your delta H. Is that a negative value or a positive value? Negative. Okay, and that's our exothermic curve. All right, we are going to make some teamwork happen. I've got a bundle of papers to pass out, so I want to make sure I have everything up to date for you as much as I can, and then we're going to talk about the lab. Okay, so all hands on deck. I need some help. I'm going to stand right here and get out the bundles. Share the lab with somebody, and if it's not our class, then you know what to do. Put in the box for the other class. If somebody doesn't have papers, then make them get up and help you. Make them get up and help you. Either find the person, or if you don't know where they sit, on the bottom of your stack and come back to it. And if you're just looking for papers, go steal half the stack out of somebody's hands. It's not our class, it's our class, it's our class, we're not here for an hour. What's your name? He's up here. Tracy's right here. Take it out. Get a laptop. We got some stuff to do. Toby's in fourth period. You can look at
Chris was right, like,
you opening it up?
In the middle. 20 years.
Our laptop will be something necessary. I wrote one. Cameron got a special signature, guys. Cameron got, if you can't read it, it's Cameron's. It says like C with an R and you can't read it. But one day he'll be famous and you'll know his signature. Because hopefully he won't change it. Alright, if you have a bunch of papers, give me a couple. If you have like 3, you can continue passing the 3 out you have. Anushka. Yeah, you get those. Alright, we're going to find a seat in like 5, 4, 2, and everybody look over their progress report right now. There should be a half sheet worth of big egg shots. You know, Alright, so at this point, find a seat. I do want anybody who has missing work to make it up. If you have questions on where it is, I can direct you there. If you have no missing work, which is like over half the class, you're getting ready to do the lab. So pull out a piece of paper for the lab. If you have missing work, maybe it's you just never turned it in. Maybe it's something you need to submit to me by the end of class. Most of the stuff should be like complete. Everything's really complete now. We are almost done with energy. Alright, so if you're doing the lab because you have no missing work, get a piece of paper out and call it Energy of Food Lab. Right now, please stop talking because everybody's got to be with me on this one, okay? I try to just put like a check on those of you guys who had nothing missing. So, when we get back to the lab, you're going to read and complete the couple of pre-lab questions first. There is a data table that would be beneficial for you to prepare, which is on the lab sheet itself. I will caution you, all the measurements have to be very accurate because we are looking at very small differences. So the smaller the difference, the bigger the error, which makes a really large % error whenever you go about that. And obviously we are going to be burning food. This is my caution. If it starts to smoke a whole lot, we are not setting off the fire alarm today, okay? Not today. So put it out with a squeeze bottle, and I'll give you a different source of food because obviously that one is just a really smoky burning food, okay? If you have time, we're going to try to do 2 trials on your food so that you can actually see if your data is valid, but we'll kind of see how much time we have. The equipment that I'll be providing you is an aluminum can, which will actually serve as a source of energy measurement. We're going to look for how much energy is transferred to water in the aluminum can. You have your food pieces that do not have marshmallows. Water, thermometer, and matches are a lighter. So what you're going to do, this image is horrible, so we maybe sketch this a little bit better for you. And if you want to sketch the diagram, it might help you with setup. You have your ring stand, right? And that's going to have your ring on it. The smaller ring is better because the aluminum can has a small base. So the aluminum can will sit on the ring, and our food source is going to be put on a little ghetto paper clip that's been kind of angled off the ground so that our burning food is not sitting on the table. So it's going to be like a little paper clip with our like Dorito chip on it, okay? And it's going to be really close to the bottom of the can, like super close, like an inch. Because what you can imagine is if you're burning this food and it's flamed up, right? Is all the heat going to just go directly to the water that's in the can? Is it? No, it's going to go here and up and down. It's going to go everywhere. So if we have it super close to the can, hopefully, cross our fingers, all the heat is transferred directly into the water in the can. So there will be 50 milliliters of water in the can, and before the experiment starts, you will have measured with the thermometer. You have gotten your temperature initial of the water, and what do you think you're going to do over the course of the reaction, over the course of the burning of the food? So you monitor what? Right, and you have to watch it really closely because you know the thermometer kind of has the markings everywhere. So if you can pull it in and out of the water, do that as minimal as you can. But you will look for a temperature final of the water. And what are you assuming has caused that temperature increase? Right, the combustion of this food. So what you're correlating is energy that was released to the water came from food. Food then has that energy, and you can calculate from there. Okay, so for those of you ready, go ahead, choose goggles, get a partner. I'll start putting stuff out in the lab. Go back to the back and go top. Can you turn some top? Just turn some top. Okay. I didn't have to go back to the back. It doesn't need to be printed, okay, because that's the thing I need in the box, because I get the emails. Okay. Get another laptop, yep. Whatever.